Hey there, and welcome to lesson 2 of the grade 12 university physics course. So we're looking at uniform acceleration some more in a new type. Let's just look at the VT graph of the type and the wordy description, and we'll call it what we see it to be. So we've got a car, the blue one here, car A, starting at 0 velocity, going up to 15 meters per second, and then traveling at a constant rate. So it says car A and car B both start from the rest of the same location. That's additional information that's not really in the graph. Car A increases from uniformly to 15 meters per second in 30 seconds, and then continues at that final velocity. Right, so there it is. And car B increases to 20 in 70 seconds. And then uniformly increasing its velocity as well, and then continues at that final velocity. So if we're looking at that situation, we know they start from rest, and we know that car A, by the picture here, you can see like accelerates more. If you did the numbers too, you did 15 divided by 30, and then you did the 20 divided by 70, the 15 divided by 30 is a bigger slope. Okay, so if it wasn't obvious, if you're just trying to graph it or whatever. And so car A stops accelerating, and then car B continues to accelerate and ends up going faster. And so the idea is it'll eventually catch up, right? So these are catch-up questions, okay? So we're looking at how to work through catch-up questions. Typical questions are, determine when and where car B catches up and overtakes car A, kind of thing, when they're at the same spot or back to the same spot, you might think of it as. And then we can also look at when they have the same velocity. So we'll tackle the spot first. One thing that's a good check about things here is just to see, to make sure that it's a simple case where it's going to catch up at some point while they both are traveling at a constant velocity, right? That's the hope. That's sort of the easier case. And so what you can do for that is you can calculate. I'll stop here. What you can do for that is you can calculate how far the car A goes in this 40 seconds, right? In this total of 70 seconds, right? So you see the 1/2 of the base times the height. That's really the area of this triangle here, right? Giving you how far car A goes in 30 seconds. And then we have that, left over time, the 40 seconds, traveling at 15. So again, the area of the graph for that. So we get a grand total of 825. The car B, the red one, or in the 70 seconds here, its displacement would only be 700. And so you can see car B is still behind. It's car A is still ahead by 125 meters. Okay, so car B will catch up at some point later. And so our work is going to be based on that fact. All right. And so the areas here are kind of nice to think of, right? Think of this area, this green area, sort of in this area. I'm trying to point to it, but I forget you can't see me. So that area there is, more displacement forward than car B. And then car B starts to have more displacement forward. You can see this little green triangle is not going to be as big as that one, right? So you're going to need some extra area, right? So that's kind of a way to visualize things as well. It's kind of nice that VT graphs help with that. And so to answer this main question here of determining when and where car B catches up to car A, the key would be, of course, when they're passing one another, they're at the same spot. Their displacements are the same. So we're going to set them to be the same. And so we're going to have an acceleration section, which you can use the UASIM, the equation selection matrix business, or you can use area into the VT graph. And I'm defaulting to area into VT graph because it's so easy, so straightforward. So just adopt and use that, or insist on using equations. You'll get the same answers. Just I'll be done before you. And probably make less mistakes because it's just so intuitive. You're looking at the numbers, right? Anyways, so the triangle would be 1/2 base times height, which we already did, but 1/2 the 30 times the 15, right? Right here. So that's the area of that triangle. And then we've got the area of the rectangle, okay? Now notice that I've defined the time, like the t variable that I have in this for, some amount of time later. I've defined it only from after that 70 seconds. And I think I had it the other way around. I'll show the other way around as well. I had it the other way around in my first go at this, and I found the algebra just looked a little messier than this. And I'll show you both, though. You can decide how you want to define the variables. So right now, this is just one variable defined right here, just that additional time, right? Which means that the length of this rectangle is from 30 all the way to the end. So it's that 40 plus t. Okay, so that's the weirdest part of this one. Then the red triangle is going to 1/2 the base times the height of it. So it's the base of 70 and the height of 20. And then the rectangle for it's nice and simple. It's just 20 times t, right? The height of 20 times the t. So base times height. Anyways, run some numbers and we'll have a t that's left over. So when we run the numbers, you can see the distributive law would multiply the 15 onto both of those, giving you the 600 and the 15t. And then I've got algebra steps peppered here where we take away 15 from both sides. That's going to be 5t, and take away the 700, collect the 700 and the 600. When I did the numbers here, I didn't even use a calculator because negative 700 and 600 becomes a minus 100. So minus 100 from that, you get a 125, right? So divide both sides by 5 and you get 25. Okay, so that's 25 seconds right there. So a grand total time of the 25 plus the 70, of course. And so you can answer that car A catches up after 95 seconds. Okay. If we wanted to look at where they catch up, you can analyze either displacement, right? Displacement of car A or car B. So really just putting the time in as 25 and calculating out. You get they catch up after 1,200 meters. All right. You might have noticed based on our original check that we did, right, this idea here, we might notice that really it just needs that extra 125 meters, right? So this little extra area here beyond this time just needs to be 125. It's another way of thinking about it. It's not how I'd recommend sort of tackling it right from the get-go for other reasons you'll see later. But really it's faster by 5 meters per second. And so how long is it going to take to go 125 meters? It's pretty simple math, right, to do with that. We want this area to be 125, so an unknown time times 5. And we're dividing by 5, and we're getting that 25 number still, right? So you can see that you're still going to have that 95 seconds. Okay, so it's just a totally different approach, but I think this is a little bit of in this case, it made sense or whatever, but the basic way of just going through it right from the start is probably your best bet overall. The other variable choice we could have, we had the additional time t there, this one, exactly as before. We could have, and it'd be tempting to have, that's why I did it as my first go at it, is I had, I want to know the total time to catch up. So I called that a variable. And so, what that forces you to do then is to have this rectangle here be that total time take away 30, right? So this is 30, the whole thing. Not sure if you can hear me over the bell, so I pause there. The whole thing's t, take away the 30 bit, you've got the leftovers, right? So that's this one. And then for this one here, the whole thing's the purple t, and so it's going to be 70, take away the 70, right? So yeah, it works. Like it's the same stuff. You get the algebra just looks a little different, right? But I mean, you get the 95 seconds either way. This one, of course, gives the 95 directly, which is kind of nice. But I felt like I had too many variables at the start here. So I had, you need to know this time interval, and so I had that in as delta t1, and then of course that's the delta t minus 30. The whole delta t to take away 30, and so on. So I think it's just valuable to see both options, I guess. And of course, you could check the displacements, and it all works still. The next one we're going to tackle, press pause, of course, and digest and write stuff down, but I'm just getting this done on the video. So the trickier case would be if it actually catches up while it's still accelerating. Okay, and so if you went ahead and made the same assumption, which is not true, obviously, if this car B accelerated forever, they would have to meet at some point. It would have to catch up at some point while it's still accelerating. So what's wrong in our assumption here on this side is we're saying, oh, well, the displacement is represented by a triangle and a rectangle. In this case, there just isn't a rectangle really, right? You can plug the numbers in, though, and do some calculations, and it'll spit out an answer that doesn't really mean anything to you as an answer. It's not actually meaningful in the question. It's not correct in any way. So you could think of it as it's supposed to be over here, right? It's supposed to be this number t, and you can see it's only 38.3. So it's like that's not working. Okay. So how do we actually do this question? Well, we first of all set it up correctly, right? Where we have the blue car, the car A or whatever is represented by a triangle and a rectangle for its displacement. Or, like you said, could be a velocity equals distance over time equation here and the appropriate uniform acceleration equation here. Anyways, we end up with the other side, though, just being the triangle, of course, right? So we need to have this delta V. We need to have this delta V somehow, like that red delta V. We're looking for it, right? So what I'm going to remind you of is that, of course, we're talking about a uniform acceleration situation, right? We've got an acceleration of 80 over 60, right? Well, we know acceleration equals delta V over delta T. So the delta V is, it's this right here. So I could put the acceleration in as the 80 over 60. That's what this little bracket here is, right? Pointing out that the 80 over 60 is just delta V over delta T. And yeah, so if I multiply delta T across, then I'd have delta V as this thing right here. So assume that orange with the symbol on top of it. We have this thing right here. That is delta V, right? So that can go in there. And that's what this next line is going to have. Get the computer to catch up to me here. So that leads to a quadratic. I'm not running through the whole quadratic formula here, but it's something that obviously needs to be able to be done if needed, right? Spits out an answer of 6.3 seconds, which that doesn't make any sense because it's an inadmissible answer, they call it. And then the correct answer from the situation is the 23.66, which we could check because we could just calculate where they are after the 23.66, and it works out to be 374 for both the vehicles. Okay, so that's a classic catch-up question. And so the way I did that was physics. I looked at we wanted delta V. I thought to myself, what relationship do I have that has delta V in it? Acceleration equals delta V over delta T, and I used some algebra skills and substituted it in. Maybe you might have looked at this and said, well, wait a minute, I'm good at grade 9 math. I know this is an equation of a line here, y equals mx plus b. So that's another way of tackling this. You could say, okay, well, this line right here is y equals mx plus b, and that's when they're meeting, right? And so the y's the v's and the x's the t's and the slope's the acceleration, right? So I can actually have my v equals the 80 over 60 t. And so that 80 over 60 t can go in as that y value. And it's just, the same as what we did before. It's just, kind of noticing that this delta v equals 80 over 60 delta t is really the slope times the x variable. Okay, so that's just noticing that grade 9 math connection, which is kind of a nice little throwback to grade 9. It's, you don't have to do that way, but you could, right? All right, next one here then. Hopefully you're good with that. This next part here is determining when they have the same velocity. So I want you to look at this. Pause the video, look at this, think about how you would do this, right? So hopefully you're unpausing at some point here, and what kind of information, maybe for hints, you press pause, unpause or play for a bit and then pause. What's the known info we have to work with, right? So you're maybe still drawing a blank, and then you press play and you see well, it's a uniform acceleration situation, right? Specifically for car A, it's the one that's uniform acceleration the whole time, right? So what do we know about car A? So you're pausing, you're thinking, and then if I remind you of the whole, the key variables that we're talking about in uniform acceleration, v1, v2, acceleration, delta t, and delta d, then maybe you start to put some numbers in. The initial velocity is 0, right? The final velocity is 20. Acceleration is the 80 over the 60, right? We've got all three of those in there. You can solve for the delta t and the delta d. So that actually can give you when and where, right? So it's I think back when this page was blanks and with these and fill in, I could see maybe pressing pause and looking at it and being unsure. But I really want you to see like this is powerful. If you notice those variables, you start ticking out which ones you know, all of a sudden you're going to find yourself able to do the question, right? So all the numbers go in, pick an equation, plug it in. Gives you, they meet after, or that, sorry, they're going the same velocity after 15 seconds. Yeah, that's all it is. And then if you want to find out when and where, you just get the areas, of course, right? So good enough, I think, for that. The next one here, a little bit of a one more trick kind of challenge thing. Like, what if they don't start at the same position? Um, so in drag racing, if you're watch this kind of thing, there's used to be a show called like Pink Slips or something like that. It was called, and if two people are drag racing for a prize or whatever, they might they want the contest to be about who the better driver is, about who's shifting better and so on. So they might actually have like numbers about the car itself, and they give the person driving the slower car a head start, right? A certain number of car lengths, and they negotiate that, and then they agree to it, and they were actually the winner. The prize was the other person's car in that show. Anyways, long story short, here though, or maybe short story long, the in this long distance race, Michael's running at 3.8 meters per second. He's 75 meters behind Robert, who's running at a constant velocity of 4.2. If Michael, manages to get a second wind and accelerates at 0.15 meters per second squared, how long will it take him to catch up to Robert? Okay, so you have this like 75-meter like difference on top of the complication of the slower one trying to accelerate and catch up eventually. So this solution I have just written out in pencil because of where I was when I was writing it out. So I'll go through it with you. Okay, so here's the given information, of course, and if you did a VT graph, that's certainly going to help visualize things, right? So we've got this kind of situation. If you're thinking this through here, the first portion, itemized as number 1 there, that's the first portion of the race where Michael, the slower runner, is falling further behind for a while still, right? Just because he's accelerating doesn't mean he's all of a sudden catching up. He's still going slower than Robert, right? So he's falling behind further, and then section 2 would be catching up to being that 75 meters behind. And then section 3 would be like this, needing to travel another 75 meters. So what you want to have is their overall displacements be the same, right? But you basically need overall resulting, I guess I should say. That's maybe the wrong wording there, but basically we need this to be bigger, right? We need Michael to go farther. So Michael's going to go Robert's distance and an extra 75 meters. And that'll make Michael catch up, right? So really we just do the same work as normal, right? We have Robert, in this case was just a uniform. It obviously could have been accelerating at first too. It's just, it was more complicated in one way. So it's simplified in another way just to make it a little easier. But yeah, so if you add that 75 on, you do the math, you get a quadratic, you solve, you get your time and so on, right? It works out. So basically the quadratic formula is spitting out a negative 29 for time. Clearly that's an inadmissible solution. Like it's a quadratic answer that doesn't have meaning in this case. And then the 34 seconds would be the one, right? So you could plug that in and get the displacements and so on. But yeah, so hopefully that is helpful. And practice questions, of course, to be completed and submitted. And let me know if you need any help. All right, talk to you later.